Hello, welcome back to Physics 141 Online. I'd like to do a short example problem that illustrates a type of problem that you'll see occasionally in homework assignments that I call an elevator problem. And here you can see the problem says a girl with a given mass stands on top of a scale inside an elevator. Calculate the reading on the scale, which is her apparent weight, while the elevator starting from rest reaches a downward speed of 6 meters per second in 3 seconds. So we need a sketch, right? We need to identify that this problem is a Newton's second law problem, right? We're going to use the second law because the problem deals with forces and accelerations, but we have an accelerating system. So we need a sketch, and the sketch looks something like this. Very crude sketch, just shows the elevator as a box, and inside the elevator there is a scale, right? And on top of the scale is the girl who's riding in the elevator. Now the elevator itself, right, is moving downward, and there is going to be some kind of acceleration downward because it says that she starts from rest and reaches a downward speed 6 meters per second in 3 seconds. So we'll figure out what that acceleration is in just a minute once we've solved the problem. But there is a downward acceleration, and as I usually do, I'm going to take the positive direction to be upward. So the y direction, x direction, whatever you want to call it, is in the upward sense, and that will determine the signs of the forces and the sign of the acceleration that we calculate. Now, in order to understand what's happening here, we have to identify two different forces. Okay, the girl standing on the scale. So she exerts a force on the scale, and the scale exerts a force on her. So I'm going to call N, I'll use that as the symbol for the force of the scale on the girl. And of course that's pushing up because the scale pushes up on her. N prime I will call the force of the girl pushing on the scale. Now by the third law, Newton's third law, we know that those two forces are equal and opposite to each other. So the magnitudes are the same, but they're in opposite directions. Which one of those is the one that we're asking for when it talks about the reading on the scale, which is her apparent weight? Well, the reading on the scale, the way scales work usually is there's some kind of a spring or other device that senses force. So the force that the girl pushes down on the scale, that's what the scale will read. And so this here, what I've indicated as N prime, that will be the scale reading. But since, of course, N prime and N have the same magnitude, if we find N, then we will know the scale reading as well. All right, so that's the important part in setting up this problem. So now we go ahead and draw a free, I'm going to abbreviate this, a free body diagram for the girl. All right, and that's easy enough to do here. With the girl, we've got the force mg, which is her weight. That's, of course, downward. The force of the scale pushing up on her, that's N, and that's all there are. Those are the only forces that are acting on the girl. So we're ready, pretty much having done our develop step. We've developed an understanding of what the problem is asking for, right? We're trying to find N prime, and we've written down a sketch for the situation as well as the free body diagram. So now we're ready to go ahead and evaluate the answer using Newton's second law. So we add up the forces in the y direction, and that should be equal to the mass times the acceleration in the y direction. And I'll just put a subscript y on there. So on the left-hand side, we add up the forces. Well, there's a positive force, which is N. Then there's a force directed downward, which is mg. That's all we have. So that's equal to m a sub y. And then N is mg plus m a sub y. And the reason that basically this gives me my answer is because, again, I know that n and n prime have the same magnitude. So if I can evaluate the right-hand side, that will give me the scale reading. But what do I need to evaluate the right-hand side? I know the mass, but I don't know the acceleration. However, I'm given enough information to figure out what it is. So before I go ahead and do that, let me just factor out m, which will make plugging the values in a little bit easier because I only have to plug in the mass once instead of twice. So how do I get a sub y? To get a sub y, use the given information and the appropriate kinematic equation. So what are we given? We are given Vy, right? That's the final velocity in the y direction. It says it reaches a downward speed of 6 meters per second, so Vy is negative, not 60, it's negative 6 meters per second, and the sign is very important. Vy0, which was the initial speed, is 0 because it says the elevator starts from rest, and the time is 3 seconds. So we want to find a sub y, and we need an equation that involves Vy, Vy0, and t, so we will use the equation Vy equals Vy0 plus ay times t, the very first of the kinematic equations. Vy0 is equal to 0, so that term drops out, and we can solve by dividing both sides by t. Ay is equal to Vy over t. And of course, now I might as well go ahead and plug the answers in, the values in, because I want an expression for ay. I want a number that I can plug into the equation for the normal force. So Vy is negative, right, 6 meters per second. T is 3 seconds, and so a sub y is equal to negative 2.0 meters per second squared. All right, and that's great. Now I have a value that I can plug in over here. So N is mass times g plus ay, so it's 50 kilograms, times g, which is 9.8 meters per second squared, and then plus ay. Well, ay is negative, and so the sign is critically important. I've got to make sure that I get that correctly. Clearly it makes sense because the elevator is accelerating downward. It's going faster in the downward direction. So when I evaluate this, I get an answer of about 390 newtons. So that's my answer. That is her apparent weight. Compare that, right? Compare to what the answer would be if the elevator were at rest. So if elevator had a sub y equal to 0, right, then of course the answer would simply be, n would simply be 50 times 9.8. There would be no acceleration, so 50 times 9.8 gives 490. And so this would be 490 newtons. So you can see that her apparent weight, if the elevator is accelerating downward, is smaller than what her normal weight would be if the elevator were not accelerating. And I think that makes sense. Many of you have experienced that before if you've been in a tall building taking the elevator down, and in the very initial instant when the elevator begins to move and accelerates downward, you feel a little bit of a weightlessness just for an instant in your stomach. Once the elevator reaches a constant velocity, then acceleration goes back to being 0, and you feel your normal weight again, which would be the 490. And then when the elevator reaches the bottom and it begins to slow down as it reaches the destination, in that case the acceleration would be upward. And then you feel heavier. Your apparent weight increases. So you can have both situations happening on a single elevator trip. But for this problem, the acceleration was downward, which meant that the apparent weight was less than the person's actual weight. I hope this helps you attack elevator problems like this. There's not too much more that we can do here. The assess step would simply be perhaps to look at the units, kilogram meter per second squared, the units, check out, because that's what newtons are, and we expect that because we're solving for a force. All right, I'll see you in class.